What if everything, the birth of space and time, the rise of stars and galaxies, the evolution of life, the emergence of human consciousness, unfolded not across billions of years, but within a single calendar year? Imagine compressing all 13.8 billion years of cosmic history into just 12 months. This is the cosmic calendar. On this scale, each month represents a little over 1 billion years. Each day spans nearly 38 million years, and every second counts for more than 400 years of real time. Human history doesn't even register until the very end. We arrive not at noon, not at dusk, but at the very edge of the calendar, mere milliseconds before the year ends. The universe spent 364 days preparing for us, and we've only just opened our eyes. To understand how we got here, we have to go back, way back, to the very first moment of the year, the moment the universe itself was born. January 1st, the birth of time and space. The universe begins, not with a bang, but with an expansion. From a point smaller than a proton, space and time erupt into existence. In the first 10 to the negative 36 seconds, the universe undergoes inflation, expanding exponentially, faster than the speed of light. What was once unimaginably small now spans trillions of kilometers. This early universe is smooth, nearly uniform, but not perfectly so. Tiny quantum fluctuations, ripples in the density of matter, will become the seeds of all cosmic structure. Temperatures are mind-bending, over 1 million billion degrees. Quarks and gluons bounce freely in a dense soup of pure energy. But even now, order begins to emerge. Within the first microseconds, quarks are confined into protons and neutrons by the strong nuclear force. Within the first 3 minutes, nuclear fusion begins. Protons combine with neutrons to form light nuclei, mostly hydrogen, some helium, and trace amounts of lithium and beryllium. But it's too hot for electrons to bind to these nuclei, so atoms can't form yet. The universe is blinding, opaque, and hostile. January 10th, light is set free. For nearly 380,000 years, photons scatter off free electrons, unable to travel far. The universe is a thick plasma, glowing white-hot and impenetrable. But as it expands, it cools. Temperatures drop to around 3000 Kelvin, cool enough for electrons to settle into orbits around nuclei. Atoms are born. With electrons now bound, photons travel freely for the first time. This moment, called recombination, releases a burst of light that still echoes today as the cosmic microwave background. It's the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old. To this day, it bathes the universe in a soft microwave glow. From here, darkness reigns. No stars exist yet. Gravity begins its slow, tireless work, clumping matter together in the densest regions of space, guided by the quantum ripples stretched out during inflation. Late January to February, first stars and galaxies. Around 200 million years after the Big Bang, gravity succeeds. In the densest gas clouds, hydrogen collapses inward under its own weight. Temperature and pressure skyrocket, and deep in the heart of the first halos of dark matter, nuclear fusion begins. The first stars ignite, massive, blue, and short-lived. These are population 3 stars, made almost entirely of hydrogen and helium. With no heavier elements to cool them, they grow to hundreds of times the mass of our Sun. They live fast and die spectacularly, exploding as supernovae and spewing the first heavier elements into space: carbon, oxygen, iron, the raw ingredients of future planets and people. These early stars begin the long chemical evolution of the cosmos. Their explosions trigger the formation of more stars and carve the interstellar medium with shock waves. As star formation spreads, galaxies begin to form, vast gravitational islands of stars, gas, and dark matter. By February, the first primitive galaxies, small, irregular, chaotic, light up the universe. Over time, they merge and evolve into spirals and ellipticals. The structure of the cosmic web emerges, vast filaments of galaxies separated by enormous voids. By March on the cosmic calendar, the universe is roughly 3 to 4 billion years old. From a God's eye view, it is a vast tapestry of structure. Hundreds of billions of galaxies suspended in a cosmic web, tracing the outlines of ancient quantum fluctuations stretched out during inflation. Between these galaxies lie enormous voids, spaces so wide and dark they can span hundreds of millions of light years without a single star. But in the denser regions, where matter clumped more tightly, gravity has been hard at work. One of those regions, a slightly overdense knot in the web, has slowly been drawing in gas, dark matter, and smaller satellite galaxies. It doesn't have a name yet, no spiral arms, no sun, no Earth. But it's beginning to coalesce into something magnificent, the early Milky Way. At this stage, the Milky Way is just a messy cloud of stars and gas, an irregular, unshaped blob that astronomers call a protogalaxy. Within it, stars are forming rapidly. The gravity of dark matter halos, those invisible scaffolds made of a mysterious, unseen substance, gathers gas into rotating disks. Shockwaves from supernovae sweep through the interstellar medium, triggering new waves of star formation in their wake. This infant galaxy is violent and unrecognizable. It collides and merges with other protogalaxies in a series of cosmic smash-ups. Each collision adds stars, gas, and momentum. Some stars are flung into intergalactic space. Others settle into stable orbits, forming the beginnings of a flattened disk. In the galactic center, something terrifying and powerful is taking shape. A supermassive black hole, millions of times more massive than our Sun, has already begun feeding on matter. As stars and gas spiral toward it, they release immense amounts of energy, flaring into quasars visible across billions of light years. Eventually, the black hole quiets, but it remains a permanent fixture in our galaxy's heart, Sagittarius A. Over time, the Milky Way starts to spin itself into order. Its disk flattens, rotating like a giant whirlpool of stars. Spiral arms begin to emerge, patterns carved by gravitational resonance, not physical structures, but waves of density. These arms are where most of the new stars form, shining brightly in blues and whites. In contrast, older stars linger in the central bulge and outer halo, glowing red and orange. Among the oldest inhabitants of this forming galaxy are the globular clusters, dense, spherical swarms of ancient stars, some of them over 12 billion years old. They orbit the Milky Way's center in wide, looping paths, relics of the galaxy's earliest generations. Meanwhile, clouds of gas and dust continue to drift through the galactic plane, the raw material for future stars and solar systems. One of those clouds, still nameless, still unborn, will, billions of years later, collapse to form our Sun. But for now, it's just stardust. The galaxy is also assembling its neighborhood. Small satellite galaxies like the Fornax and Sculptor dwarfs fall into its gravitational embrace. Some are shredded, leaving behind stellar streams, ghostly trails of stars that still arc across the halo today, evidence of ancient mergers. By the end of March, the Milky Way has taken on a familiar shape, a barred spiral spanning over 100,000 light-years across, with upwards of 100 billion stars and uncountable planets. It has settled into its identity. It is one galaxy among perhaps 2 trillion in the observable universe, but it is our galaxy, our birthplace, our home. Everything that will ever happen to us, every sunrise, every breath, every civilization, will happen within this one vast spiral of light. And still, the stage is only half set. The Milky Way will continue to evolve, but it is ready to host solar systems, ready to nurture life. And in a quiet, unassuming arm, 9 billion years after the Big Bang, a small yellow star will soon begin to shine. August 28th, the Sun is born. Around 4.6 billion years ago, in a quiet arm of the Milky Way called Orion's Spur, a cloud of gas and dust collapses. Possibly triggered by a nearby supernova, the cloud spins and flattens into a disk. At its center, a new star ignites. The Sun. It's a G-type main sequence star, destined to shine for 10 billion years. Around it, the disk begins to fragment. Dust grains stick together. Centimeter-sized particles grow into kilometer-wide planetesimals. These merge into protoplanets. Over tens of millions of years, collisions forge 8 major planets, including one rocky, water-bearing world 93 million miles from the Sun. It is now early September on the cosmic calendar. Roughly 9.2 billion years have passed since the birth of the universe. The Milky Way, our home galaxy, has matured. Its spiral arms are well defined, its central black hole quieted but still ravenous. Stars are forming by the millions, dying by the millions, constantly recycling the elements of life. In one of its spiral arms, an ordinary molecular cloud begins to collapse. Triggered perhaps by a nearby supernova shockwave or the gentle tug of gravity over millions of years, the cloud flattens into a rotating disk of gas and dust. At its heart, pressure builds, hydrogen fuses, a new star is born. That star is our Sun. Surrounding it is a chaotic maelstrom of matter, a protoplanetary disk stretching billions of kilometers across. Inside this disk, dust grains begin to stick together through static electricity and gentle collisions. Over thousands of years, these grains form pebble-sized rocks, then boulders, then planetesimals, kilometer-wide bodies large enough for gravity to take hold. These planetesimals don't grow peacefully. They smash together at thousands of kilometers per hour. Some are pulverized, others survive. Over tens of millions of years, the survivors sweep up more material, growing into protoplanets, embryonic worlds jostling for position. Among them is a third planet from the Sun, not the biggest, not the fastest, but one day it will become something extraordinary. This is Earth, and in these early days, it is nothing like the blue marble we know. The young Earth is a molten inferno, heat from constant impacts, residual energy from its gravitational collapse, and the decay of radioactive elements keep its surface churning like a sea of fire. There is no solid crust yet, only oceans of magma, waves of liquid rock glowing red and orange under a dense toxic sky. Around 4.5 billion years ago, a cataclysm occurs, one that will define Earth's future forever. A Mars-sized object, often called Theia, slams into the Earth at an oblique angle. The collision is apocalyptic. Mountains vaporize, oceans of magma are thrown into space. For a moment, Earth and Theia merge into a single, deformed mass. Debris from the impact escapes Earth's gravity and forms a glowing ring of rock and dust encircling the planet. Within weeks, This debris coalesces into a sphere, the Moon. The Moon begins in a much closer orbit than it is today. It looms large in the sky, tens of times larger than we see it now. But its presence is no mere ornament. It stabilizes Earth's axial tilt, preventing chaotic wobbles that could have caused wild climate shifts. It slows Earth's rotation, lengthening our days. It sculpts the tides. Without the Moon, the conditions for life might never have taken hold. Over the next tens of millions of years, Earth cools. The outer layer hardens into a brittle crust. Volcanoes burst through it constantly, releasing carbon dioxide, methane, ammonia, and steam into the sky. The atmosphere is thick, choking, and unbreathable by today's standards, but it's beginning to form the greenhouse blanket that will warm the planet and protect its surface. Rain begins to fall, perhaps for centuries. Water vapor condenses in the high, acidic clouds and crashes down onto the scorched earth. The planet steams and hisses, absorbing the deluge. Valleys fill, basins collect. The first oceans are born, forming vast planetary mirrors that reflect the glow of a still-forming sun. We don't know exactly where the water comes from. Some of it may have bubbled out of the mantle. Some may have been delivered by icy comets and asteroids. But by 4.4 billion years ago, Earth already has liquid water, a crucial ingredient for the story to come. The continents don't exist yet. Instead, Earth's surface is a shifting patchwork of volcanic islands and basaltic plateaus. The crust is thin, weak, and constantly recycled by tectonic movement. Beneath it, the mantle churns. The core, composed mostly of iron and nickel, solidifies and begins to spin, generating a magnetic field that shields Earth from deadly cosmic radiation. It is another invisible guardian of life. The sun, meanwhile, is young and volatile. It flares frequently, blasting Earth with solar wind. But our magnetic field deflects the worst of it, creating auroras in skies no human eyes will see for billions of years. Somewhere in these early oceans, lightning strikes a primordial soup of chemicals. Heat vents at the ocean floor release mineral-rich fluids, and in these harsh alien conditions, something happens that has never happened before. Simple molecules organize into self-replicating structures. They are not yet alive, but they are the beginning. The Earth is ready, not for us, not yet, not for fish or ferns or dinosaurs, but for the first whispers of life, invisible, fragile, and unstoppable. The story of a planet has begun, not as a passive rock in space, but as an active, evolving system. A world that will one day sing with oceans and forests, thunder with the hooves of beasts, and light up the dark with the minds of creatures who can tell this very story. But for now, it is only silence. The long wait for life begins. September 21st. Life begins, likely not as a single spark, but as a gradual transition from chemistry to biology. Perhaps at hydrothermal vents, where hot, mineral-rich water mixes with the cold ocean, creating energy gradients ideal for complex molecules to form. Simple organic compounds assemble into self-replicating structures. One of these evolves into RNA, a molecule capable of both storing information and catalyzing reactions. These first organisms are prokaryotes, cells without nuclei. They live, divide, evolve. They become more efficient. Some begin capturing sunlight to power themselves, a process called photosynthesis. The first major innovation in biological energy. For over 1 billion years, Earth is ruled by microbes. They shape the environment and eventually they change it forever. Mid-October, oxygenation of Earth. the rise of photosynthesis triggers the great oxygenation event. Oxygen, once a rare trace gas, begins accumulating in the atmosphere. At first, it reacts with iron in the oceans, creating vast deposits of banded iron. But eventually, it saturates the seas and spills into the sky. Oxygen is toxic to many anaerobic organisms, leading to a mass extinction. But it also enables more efficient metabolism and ultimately complex life. November 15. Eukaryotic cells and multicellular life. Around 2 billion years ago, a new type of cell evolves. These eukaryotic cells have internal compartments, nuclei to store DNA, mitochondria to generate energy. This likely happened through endosymbiosis. One cell engulfed another, and the two formed a symbiotic relationship. These advanced cells are more flexible, more adaptable. They become the building blocks of algae, fungi, plants, and animals. Around November 25th, multicellularity evolves. At first, it's simple, cells sticking together. But then, division of labor appears. Cells begin to specialize, tissues form, organisms emerge. November 30th, the Cambrian explosion. 500 million years ago, evolution explodes in diversity. The Cambrian explosion floods the oceans with complex life: trilobites, worms, sponges, and early fish. Nearly every modern animal body plan appears during this short 20 million year window. Eyes evolve, nervous systems grow. Predators and prey engage in a biological arms race. Life is now dynamic, competitive, and spectacular. December 5. Life on land plants are the first to colonize land, spreading across damp coastlines and slowly adapting to life above water. Vascular tissues develop to transport nutrients. Roots anchor them in soil. Soon, entire forests rise. Insects follow. Then, amphibians, descendants of lobe-finned fish, crawl onto land. Reptiles with tougher skin and shelled eggs evolve next. They conquer the continents. December 26. The age of dinosaurs. Dinosaurs dominate for over 160 million years. Their world is alien: dense jungles, shallow seas, volcanic eruptions. Some grow larger than buses, others evolve feathers and take to the skies. The first birds appear. Mammals remain small, nocturnal, and hidden, surviving under the feet of giants. December 30th, 6:24 a.m. The asteroid, a space rock 6 miles wide, hits the Yucatan. Global firestorms, ash clouds block the sun. Photosynthesis collapses, food chains unravel. In weeks, the dinosaurs, except for birds, are gone. Mammals seize the moment. December 31st, the human story. The universe is now 13.8 billion years old. It is December 31st on the cosmic calendar. For 364 days, stars have been born and died. Planets have formed and been pulverized. Oceans have stirred. Tectonic plates have shifted, and life has crawled, swum, and soared. And yet, everything we think of as history, every human face, every word written, every war waged and peace made, hasn't happened yet. Until now. On this final day of the cosmic year, somewhere around 10:24 p.m., in the grasslands of East Africa, an ape stands a little taller. Its gait is clumsy, uncertain. But with this first upright step, something new enters the world: Homo erectus. These early humans are unlike any creature before them. Their brains are larger. They use tools, not just stones to smash and scrape, but fire to cook, to warm, to protect. Fire changes everything. It unlocks more calories, fuels brain growth, reshapes sleep, reshapes society. Around the fire, language begins to evolve. Not merely grunts or signals, but the foundations of shared memory and myth. Over the next 2 hours, millions of years in real time, evolution accelerates. Brain size increases. Stone tools become more refined. Groups grow larger, more social, more strategic. And somewhere between 11:30 and 11:45 p.m., Homo sapiens appear. We are anatomically modern humans. Our skeletons match yours. But in the beginning, we are just another species of hominin on a continent teeming with life. We are not dominant. We are not inevitable. And yet, we have something special. We imagine. We tell stories. Paint animals on cave walls. Bury our dead with flowers and tools. We plan hunts. We teach. We remember. By 11:50 p.m., we've begun to migrate. Out of Africa, into the Middle East, Asia, Australia. We cross ice bridges into Europe. We live among Neanderthals. Some of us interbreed. Then, mysteriously, the Neanderthals disappear. Whether by competition, conflict, or assimilation, we remain alone, but not for long. By 11:56 p.m., we've reached the edges of the world, from the Arctic Circle to the Amazon rainforest. We live in small tribes, bound by kinship, myth, and survival. And then, another great transformation. At 11:57:30, the Ice Age ends. The climate warms, glaciers retreat, sea levels rise, and in the Fertile Crescent, someone plants a seed. Agriculture begins. This may be the single most consequential experiment in human history. We stop roaming, we settle, villages form, grains are harvested, animals are domesticated, populations explode, and with surplus food comes hierarchy, division of labor and ownership, property, writing, power. By 11:58 p.m., the first cities rise: Uruk, Jericho, Babylon. Kings rule, priests advise, scribes etch stories into stone. The first laws are written, calendars appear. We mark time, we name the stars. Civilization is born. From here, history accelerates. By 11:59 p.m., the world is a patchwork of empires and cultures. In Egypt, pharaohs build pyramids aligned with celestial precision. In Mesopotamia, clay tablets record trade and myth. In the Indus Valley, cities are planned with grid-like streets and drainage systems. In China, dynasties rise along the Yellow River. In the Americas, maize is planted. Temples climb toward the heavens. Astronomy, mathematics, metallurgy all begin to flower. At 11:59:20, the Greeks give us philosophy and democracy. The Chinese build the Great Wall. Rome expands across continents. India gives rise to Buddhism and the concept of zero. Trade routes crisscross the globe, from the Silk Road to desert caravans. Languages evolve, ideas migrate, religions rise and spread. Then come revolutions. By 11:59:45, Gutenberg prints the Bible. The Renaissance awakens Europe. Newton deciphers gravity. Empires colonize continents. With ships and steel, nations conquer. Entire civilizations are enslaved or erased, but ideas survive. Resistance takes root. New societies emerge. At 11:59:55, the modern world erupts. The Industrial Revolution burns coal, spins steel, and births the factory. Electricity flows, steam powers ships, trains connect cities, the telegraph collapses time. The 20th century begins. In the final 4 seconds, 11:59:56, we split the atom. Einstein redefines time. Planes cross oceans. Vaccines save millions. World wars rage. 11:59:57, we land on the moon. Computers shrink from rooms to chips. The internet is born. Billions connect. 11:59:58, we map our genome. send probes to interstellar space. We begin to photograph black holes. 11:59:59, social media rewires society. Artificial intelligence awakens. We watch the Earth warm, and we begin to ask what's next. Every king, every prophet, every poet and tyrant, every love story, every death, every dream, all of it happened in that final second of the cosmic year. You are here, now at midnight, not even a blink in the lifespan of the universe. And yet, you are the first creature, as far as we know, capable of understanding the calendar at all, of compressing eternity into comprehension, of telling the story of time. You are the cosmos become conscious. A ripple of hydrogen atoms and stardust, building telescopes, building stories, building meaning. The year is over, and a new one begins. So now the question is, what will we do with the first second of the next cosmic year?